Hello everyone, welcome to today's webinar titled Preventing Circulating Current in Parallel Generator Applications. My name is Leah Andrew and it's my pleasure to be your moderator today. We've got over 50 registrants from around the world attending today, so thank you very much. We would like to hear your thoughts on this topic, so please ask questions and share your comments. You can use the question and answer panel or the chat panel on the right side of the GoToWebinar player to share at any time during the presentation. We will attempt to answer as many questions as possible at the end of the session. Also, feel free to submit any questions after the event via email at mirusinternational.com or join the conversation on the MIRUS LinkedIn page. Now, at this point, I would like to introduce our speaker, Tony Hoevenaars, President and CEO of MIRUS International Inc. Prior to joining MIRUS in 1996, Tony was the Chief Facilities and Electrical Engineer at an IBM manufacturing facility in Toronto, where he gained experience in solving power quality-related problems, particularly in the area of harmonics. Tony is a professional engineer, member of IEEE, and has published excellent research papers on power quality. Tony, welcome, and over to you.
Thank you very much, Leah, and good day, everyone. It's great to have this opportunity to speak with so many of you spread out throughout the world. It just goes to show that no matter where we're located, we face many of the same challenges. MIRUS has been assisting customers all over the world in resolving problems related to power system harmonics since our inception in 1991. Our foray into the parallel generator market began when customers approached us for a solution to their high circulating current problem. They asked us because they saw it as a harmonics issue, since the current was 3 times the fundamental frequency, or 180 hertz here in North America, and 150 hertz where the fundamental is 50 hertz, and many other areas in the world. We have developed a very effective solution for the problem, although, as you'll learn during this presentation, it is more a voltage matching issue than a harmonic distortion one. Anyone who has been involved in paralleling 2 or more generators will know that concern needs to be given to the possibility of circulating current in the common neutral. Or when the neutrals are not bonded together, current in the neutral to ground connections. These can be particularly heavy when the generators being paralleled are of different pitches. Preventing this has proven to be very difficult. But now there is an easily applied and very effective solution. So today we're going to be talking about generator pitches, the configurations of generators, and how that can result in harmonics. We're going to look at paralleling dissimilarly pitched generators and why that creates neutral circulating current. We'll look at a few traditional methods to prevent generator circulating current. And then I'll introduce the GenLink DPNL, which is an easily applied unique reactor for blocking the circulating currents. And then we'll review a few case studies of applications that we've done. So let's start with a brief description of generator pitch configurations and how this generates harmonics. AC voltage is produced in a synchronous generator's armature windings by the generator's rotating magnetic field. Although a perfect sinusoidal waveform is the goal, some distortion will always be present. The configuration of this distortion is influenced by the generator's winding pitch. Winding pitch is the ratio of the coil pitch to the pole pitch, and coil pitch is the angular displacement between the 2 sides of the individual coil winding. So we can see the coil started at this location and then wound a full 90 degrees. This would be a full 100% coil pitch. Pole pitch is the angular displacement between the magnetic poles of the rotor or whatever is rotating that magnetic field. For a 4-pole generator, the angular displacement is 90 degrees. A full pitch generator is going to be one where the coil pitch, like a 4-pole full pitch generator, is going to have a coil pitch of 90 degrees, which matches the pole pitch of 90 degrees, and the ratio being 1. But most generators are built with fractional pitch windings. And the main reasons for this is that you can reduce the copper in the windings by going fractional pitch, so the length of the winding is much shorter and doesn't go the full 90 degrees. And also, it turns out that fractional pitch windings actually are more sinusoidal than full pitch configurations, so there's less harmonics that's created. So this example shows a 2/3 pitch where the coil pitch is 60 degrees, the pole pitch is 90 degrees, and that equals 2/3 pitch, and this generator would be a 2/3 pitch generator. The table on this slide shows the relationship between a generator's winding pitch and the harmonic voltage distortion that it will produce. The pitch factors shown indicate the relative level of distortion at each harmonic. So if we look at the 2/3 pitch generator, we'll see that there's zero introduction of third harmonic in theory. However, we've got a higher fraction of fifth and seventh and ninth harmonics. So this generator would produce lower levels of third harmonic voltage distortion than, say, the 4/5 or the 5/6 generators, which have a higher pitch factor. So it's worth noting that in theory the 2/3 pitch generator should not produce any third harmonic voltage, but will produce more fifth and seventh. So the question often asked is, if a 2/3 pitch generator produces less third harmonic voltage distortion, will it be a better option for reducing circulating current that is typically triple frequency? Many would say yes, but I would argue no, and we'll explain that in a few slides going forward. The main reason for this is because the addition to the level of voltage distortion that drives the circuit, in addition to that level, a key parameter in how much circulating current will be present is the zero sequence impedance of the generators being parallel. A 2/3 pitch generator has very low zero sequence impedance, and therefore will present little resistance to the flow of the circulating currents. So although it doesn't produce much third harmonic voltage, when there is third harmonic voltage in the system, or if there's voltage waveforms being paralleled that are not in the same wave shape, then the 2/3 pitch generator provides little impedance to the flow of the circulating current, so more circulating current will flow in that application. Most generator manufacturers today now sell primarily 2/3 pitch winding configurations. So when paralleling with generators of other pitch factors or a utility transformer, the low zero sequence impedance will actually allow more neutral circulating current to flow. So why do we have circulating neutral currents when we have generators of dissimilar pitch being paralleled? This graph shows the waveforms from two generators of different pitches. One could be a 5/6 pitch generator, shown here in blue, and this generator has a higher peak voltage and slightly lower shoulders, and then the other, being a 2/3 pitch generator, I have a lower peak voltage and broader shoulders. So when we're paralleling generators and we're synchronizing the voltages between two generator systems, we're trying to match the RMS voltages between the two generators. So if we match the RMS voltage of one that has a higher pitch and lower shoulders, That area under this curve needs to be the same as the area under the curve of the red graph, the other pitch generator. So if you have one generator that has a higher pitch, in order to have the same area, you have to have lower shoulders. And opposite, if you have a lower peak, you have to have broader shoulders. So when you have these wave shapes being paralleled together on the same bus, it results in instantaneous voltages that go from 0 between the two generators up to a peak value in positive, with if you're looking at the 2/3 of the red wave shape relative to the blue wave shape, and then it goes back down to 0, and then it repeats in the opposite direction. So the red is less than the blue, and we have negative cycle, half cycle, and then a positive half cycle. So now you can see that during 1/2 cycle of the fundamental voltage, we have 3 half cycles, or 3 times the fundamental frequency. So by the true definition of harmonics, however, this is not a third harmonic. Harmonic is the result of Fourier analysis on a distorted waveform. This is simply voltage that has a frequency that is 3 times the fundamental that results from the voltage wave shapes being dissimilar. I know it's a bit of semantics, but this is what we're dealing with more, is the dissimilar voltage wave shapes. And I realize that the reason I highlight that particularly is that, we're finding that people constantly are saying 2/3 pitch is better because it doesn't generate third harmonic voltages. Well, when we're paralleling, it doesn't matter where the voltage is being generated. It's the impedance of the system that's going to either block the flow or allow the flow. And 2/3 pitch generators have less zero sequence or impedance to the flow of third harmonic. So when we're paralleling, if we have these instantaneous voltages, they're going to drive current in each phase through the phase conductors on the parallel bus back into the other generator, and then combine in the neutral, the connected neutral, and circulate this way. So every phase has circulating currents that are the result of the dissimilar wave shapes. And the total of these currents is what shows up in the neutral. Or if this was not, the neutrals weren't connected but they were grounded, then the current would flow through the ground and then back into the other generator and back. So what can we do, or what have we been doing to address this issue? Well, one easy and I guess simple solution would be to ensure that that all the generators are of the same pitch. This isn't always possible, however, because if you're connecting on a site that has existing generators, the generator manufacturer may not offer that particular pitch generator anymore. Or you might want to use a different generator manufacturer at the site. So if we can put exactly the same generators in with the same pitch, then that will reduce the possibility of circulating currents. But even identically pitched generators can have slightly different wave shapes, which can still result in some circulating current. Or we can add impedance in the common neutral. Neutral grounding resistors often are used to limit fault level in generator applications. We can have high resistance grounded systems, or we can have low resistance grounded systems. Those resistors will introduce impedance and will limit that circulating current. But they do affect the fault level. You can also use neutral reactors as well. If they're inserted directly in the neutral, then they will affect the fault level. Sometimes we want to limit the fault level, but we need to understand that that's exactly what we're doing. If we're putting devices into the system that restrict the fault level, and we're not aware of that, then we could possibly limit the faults to levels that won't allow the protection to trip. The other point is these need to be rated for the residual steady-state circulating currents. So NGRs typically are rated for instantaneous currents, fault currents, not often rated for the continuous circulating currents. So you need to put in much larger devices, much more expensive devices when you need to address the circulating currents. And of course, we can apply an ungrounded system where we don't ground the neutrals. Doing that, codes require that we be monitoring for ground fault, and we indicate that because our protection is not going to interrupt a ground fault now. Sometimes zigzag reactors are used in this type of situation to create the ground reference, but those don't always provide fault paths for internal faults in generators. So the GenLink DPNL is a multiple winding reactor that's installed in the common neutral of parallel generators or generators that are paralleled with the utility. It inserts approximately 48% impedance in the neutral circulating path at the triple frequency. So it's a very high impedance, and that's why it's so effective in blocking it. And this can reduce neutral circulating currents by 70% or more, often eliminating it altogether. There's a minimal effect on fault level, and this is intentional. So when the reactor is saturated during fault conditions, the impedance to fault currents is less than 1%. So it will not change your protection scheme or require change to your protection scheme. And it has no influence at all in the three-phase fault level. And we've built these and designed them to IEEE standard 32, which is the requirements for neutral grounding devices. There are many applications for the GenLink. If we've got parallel generators with dissimilar pitches in standalone or in emergency standby operation. Generators are other alternative energy sources that are paralleled with a utility transformer. And if we have multiple generator configurations, multiple transformers, we can do cascaded applications for the DPNL. And some examples would be alternative energy generators, standby generators, islanded supplies for drilling rigs, production platforms, pumping stations, etc. Here's an application of the DPNL in a four-wire system. We're showing two generators, one as a 2/3 pitch and the second as a 5/6 pitch. But the exact pitch configurations don't matter in this application. It's just if they're different, then you're going to get circulating current. So if it's a 4/5 and a 5/6, there'll be circulating currents. So any configuration of dissimilar pitches are going to result in the circulating currents. Now, when we have four-wire applications, if we have to bring the neutral back, so if we have phase to neutral loads downstream of the generators, then we recommend that the neutral conductors be supplied through the same conduit as the phase conductors for each generator. And that is so that the fluxes that are generated in the phase conductors will cancel with the return flux going through the neutral when we have single phase loads. And this is good common practice in any four-wire application. And the other thing that's important is that the system should be grounded in only one location. Here we're showing the ground to be at the neutral bus in the switchboard. If we don't want to ground it here, we can also ground it at the X terminal of the DPNL. But it should only be grounded in one location so that we only have one return path for fault currents. This slide shows a configuration where we'd have generators, in this case similarly pitched generators, which are then paralleled with the utility transformer. So again, in this situation, the waveforms being created and supplied by the generators can have slightly different wave shape than the voltage supplied by the utility. So we can get circulating currents. Here we show the neutral going from X connected to the neutral bus, and both the generator neutrals going through the DPNL and the transformer, the utility transformer neutral going through the DPNL. When we're grounded in one location. Same scenario, but now we have the generators are of different pitches. So we have a 2/3 pitch and a 5/6 pitch. And this is a scenario where we can do cascading arrangements. So we can do a DPNL between the two generators to prevent the circulating current between the two generators, and then another DPNL between the combined generators and the utility transformer to prevent the circulating currents between the generators and the utility. So we look at the fault path. Red lines here showing a fault. If we had a face to ground fault, one of the phases, fault current's going to go through the ground, back in through the system ground connection, back to the neutral, and across the shoulder of the DPNL, and then back to the generator. And when it circulates like this, the protection in the system will detect the fault and trip and isolate the fault from the generator supply. Fault current, as I say, passes through the shoulders, and the DPNL is designed to have 4 to 5% impedance across its shoulders. But as I mentioned before, during fault, the actual impedance during the fault that we introduce is about 1% impedance. Is that that's because the iron core of the DPNL will saturate during the higher fault currents. So this graph shows one size DPNL. This happens to be a 3,000 amp unit, and at the fault, or at the rated current of the DPNL, the impedance is just under 5% in this particular case. But as we go through higher fault or higher currents, which in a fault condition will get very, very high currents, as we get down to 10,000 amps fault current, we now have saturated the core, and our impedance is less than 1%. So we're not going to affect our protection schemes. But the circulating current is going to flow, or if there's circulating currents, it's going to try to flow between the neutral and one generator through the phase conductors, as we showed before, back through the phase conductor of the other generator, and back through the Y and Z terminals of the DPNL. So flowing through this connection of the DPNL, we have 4 times the shoulder inductance or impedance. And since the frequency of the circulating currents are 3 times the fundamental current, then if we have 4 times the shoulder impedance, and we have, say, 4% impedance in the shoulders, 4 times 4 is 16% impedance, at 3 times the frequency, that's going to be 48% impedance at the 180 hertz of a 60 hertz system. So we're inserting huge impedance to block the flow of circulating currents without introducing high impedance in the fault current path. This slide shows a an ungrounded system application. Here we have 2 generators that have similar 2/3 pitch, and then another 2 generators that are 5/6 pitch. So we can combine the generators that have the same pitches and feed that combined neutral into the DPNL also feed the neutral from the other combination of generators with the same pitch into the DPNL. We don't need to ground this. We can ground it. If it's an ungrounded system, then you have to have ground fault monitoring and all the things associated with ungrounded systems. If you want to ground it, but you don't need to connect the neutral, then you can ground the system at, or if you don't have phase to neutral load, so you don't need a neutral return path, then you can ground the DPNL at the X terminal. And in these applications where there is no return neutral current, the DPNL can be sized smaller than it would when it has to handle the return neutral current in a 4-wire application. Now there's some situations where the DPNL needs to be combined with a neutral grounding inductor. And that would be examples, what might be parallel generators with dissimilar pitch that are tied to a utility grid supplied by a transformer or multiple transformers, but where you do not have access to the transformer's grounded neutral. The DPNL will prevent circulating current between the generators. The NGI is then needed to add some impedance to block the current from the generators to the utility transformers. Again, if you're able to route the neutral, so the best configuration is to take the neutral from the utility transformer and run it through the DPNL. And in this case, you would do a cascaded system. You'd put another DPNL here, and you would run that ground through. That's the best configuration that provides the highest impedance to circulating currents with the lowest influence on the ground fault systems. So we provide sizing tables to make it easier to select the size of the DPNL for a particular application. The way these tables work is that you total up the capacity of all paralleled sources. So if you have 2 generators being paralleled, you total up the capacity of the 2 generators. If you have 2 generators with a utility transformer, you total up the capacity of the 2 generators plus the utility transformer. Either in kilowatts or kVA. You look at your system voltage rating, and then you'll select the size of the DPNL based on the size of the total generating capacity. So if you have 2,000 kilowatts on a 480 volt system, you would use a 1500 amp DPNL. The 1500 amp is the return neutral current rating. It also has a circulating current rating, and that is always going to be half of the return neutral current rating. When we select from this table, that will size the DPNL for return neutral current. That will be at least 50% of the full phase current ratings. For power systems that have more phase to neutral loads, such as a 208 or 240 volt system or a 380 to 400 volt system, we size it so that it's 85% of the power system rating. But it is the responsibility of the users that's applying them to make sure that the return neutral rating is high enough to handle the return neutral current. So if you have a lot of phase to neutral loads and you're expecting the neutral current, return neutral current to be higher than 50% in the typical applications, the power system applications, or higher than 85% in the 208 to 240 or 380 to 440, then you might need to go to one size up on the DPNL to handle that. But certainly, by far the majority of the applications, the standard ratings for neutral return current are more than acceptable. For 3-wire applications where there's no return neutral current, we can definitely select smaller DPNLs. So let's look at a few case studies. This first one is a refrigerated storage facility for McDonald's, where generators were being used for backup power. During testing, they noticed that the neutral conductors were extremely hot, and they measured 160 amps in the neutral return, in the neutral circulating between the two generators. So from the selection table, we sized that, this case, to a 1300 amp DPNL, and it was installed in the common neutral of the two generators as shown. And grounding, the system was grounded in just one location at the neutral bus. Once the DPNL was installed, we went back and took measurements. You can see the residual current and the combination of the current from generator 2 and generator 1. If we sum those two currents up, it's about 41 to almost 42 amps. And the current returning to the neutral here is 38 amps. So that difference is only 2 or 3 amps. So that's all that's left of residual circulating currents is 2 or 3 amps. This current going back through the neutral is current from phase to neutral loads in the system, which has to have a return neutral path. So there was a substantial reduction in the neutral conductors. The temperatures of neutral conductors dropped dramatically, and the generators were offloaded of this excess 180 hertz currents. The second case study is a hospital in South Florida, again with backup generators. Generator manufacturer provided calculations to show what they expected the neutral circulating current to be. And in this case, it was the same generator manufacturer, but the generator manufacturer no longer provides the same pitch configurations. So the two existing were 0.8667 pitch, and the new generator that they had to purchase was a 2/3 pitch. And I apologize for the typo here. That should be 0.667. Just notice that. So it should be 0.667. That's a 2/3 pitch generator. So you can see here in the spreadsheet from the generator manufacturer, they're expecting 90, just under 100 amps of current in the neutral on each of the existing generators, and all of that returning to in the parallel generator, the new parallel generator, of just under 200 amps. When we totaled up the total kVA capacity of two generators, it came to 2500 amp DPNL, and that was installed in the system. We didn't get a chance to go back. You can see the installation here of the unit. We didn't get a chance to go back and take measurements, but the engineer here that did the installation did say that prior to the installation of the DPNL, the circulating current was actually in the range of 400 amps, so much higher than the predicted 200 amps from the calculations. But after the DPNL was installed, they could not measure any circulating currents, so we virtually eliminated it altogether, and all of their problems had disappeared. And the final case study that I present is at a utility power station that was installing, had an existing generator that was 0.722 pitch, and they were installing a new generator at 0.814 pitch. Quite large generators, 13.8 kV system. So we installed a DPNL in the return neutral current here, and after the installation, when they went back and measured it, you could see there was still a significant amount of current. This is the current from one generator, and then the current from this second generator. So 145 amps on one, 136 amps on the other. And there was still current going through to ground. If we total the 145 and the 136, we get 281 amps. So essentially, all of the current that's coming from these generators was going through the X terminal and back through the ground. There was no circulating currents between the two generators. Problem is, 280 amps is still a high level of return neutral current. The reason that neutral current was returning was going through the utility transformer neutral to ground connections, which we weren't aware of when they approached us for the application. So to eliminate or reduce that circulating current, we would require the installation of either a neutral grounding resistor connected back here from the X terminal through to the grounding connection, or a neutral grounding inductor, or NGI, sized to block that extra flow of current. So we went through the calculations to determine that an NGR would require about 19 ohms, would have to have a 60 amp continuous rating. Size of one manufacturer's is shown here, and they predicted there would still be a residual of 50 amps. An NGI, because we're dealing with inductance, which is 2 pi FL, so 2 times the frequencies, and if the frequency is 3 times the fundamental, we can put in less impedance in the inductor than the resistor, and it has less resistance as well, so there's less losses associated with that NGI. Slightly larger box configuration, but better performance in reducing the residual circulating currents. So either of these approaches would work, but when you can't or don't have access to the transformer's neutral connection, and we need to look at adding either an NGR or NGI to the DPNL application. So in summary, when you're paralleling different power sources, you can can result in neutral circulating currents, either dissimilarly pitched generators or generators or other alternative energy sources with the utility supply, or different alternative energy sources. So anything that could have a voltage wave shape that's a voltage source generator that would have different wave shapes. The neutral circulating current is predominantly triple frequency, so on a 60 hertz it's 180 hertz, 50 hertz it's 150 hertz. We can apply a DPNL that will reduce that triple frequency circulating currents by more than 70%, without affecting fault levels. And the neutrals should be grounded at only one location. And if there are utility transformer neutrals, if they're accessible, we want to run those neutrals through the DPNL and ground the system at one location. So now we can address any questions that we may have. Before doing that, however, I would like to mention a new IEEE peer-reviewed paper that we've just published that has applications for generator installations as well. So most of you online today are involved in many generator applications. The paper is entitled Right-Sizing Generators Through Harmonic Mitigation Realizes Energy, Emissions, and Infrastructure Reductions. It was presented at this year's IEEE Petrochemical Industry Conference in Houston, and it documents the application of our passive harmonic filters on an islanded pumping station where the generator had to be substantially oversized to handle harmonics generated by the pump's variable speed drives. And in fuel savings alone, the filter was paid back in about a month and a half. In addition, the generator was later replaced with a much smaller unit, lowering fuel consumption and emissions even further. So reducing harmonics in generator applications really truly is a no-brainer in many situations. So we will be offering a future webinar on this paper and the application as well. So having said that, we're open to any questions that we may have.
Okay, our first question is, in the design phase, can you calculate or predict the level of circulating current you would expect on the system with two different pitch generators?
Well, as you saw, there was one generator manufacturer that does a model to calculate what they would expect for the circulating currents. We can apply our impedance, zero sequence impedance, into that model, and we can predict that. We don't have access. The challenge is trying to determine what the voltage levels will be, and it's even challenging for generator manufacturers to figure out exactly what the common mode voltage is, the common mode voltage that's driving that circulating current, to figure out what exactly that voltage is. But generator manufacturers do try to predict that. If we could have access to that spreadsheet, then we could insert our impedance in there and do that calculation. So it is possible. However, as we saw with the one application, even with that calculation, the actual circulating current was much higher than what was originally predicted. The beauty of the DPNL is that it inserts so much impedance without negative consequences in fault level, inserts so much impedance that virtually any level of common mode voltage is going to be blocked substantially. So we don't really need to do detailed calculations for that, and we'll still have very effective results. So it is challenging, can be done. It isn't really necessary, however.
Okay, we've got two questions that are related to each other, so I'll read both of them. Can you expand on paralleling generators with the utility transformers and the concerns with that? And the other one is, in which cases NGI must be used?
Okay, they are very similar questions. And the ideal configuration of the DPNL, where it really is most effective, is when we ground the utility transformer neutrals through the DPNL. Sometimes this isn't possible, either because the transformer is a long distance away, and it's impossible to run the neutrals, the grounding connection from the neutral all the way to the location of the generators where the DPNL is. Or we haven't been able to convince the utility that it's in their best interest to allow the neutral connection to go through the DPNL. Since we insert very little impedance, it is a safe connection, but not all utilities understand that and would allow it. So if it's not possible, that does provide a return path for these circulating currents. So in order to limit that, we would need to put in impedance in the neutral. That can be done either with an NGR that inserts impedance, or with an NGI, neutral grounding inductor. So we would recommend the NGI. The NGI, because we're dealing with inductance rather than resistance, the NGI presents higher inductance at 3 times the frequency than it does at the fundamental frequency. So again, it'll block that return current without affecting the fault level as much. So those installations, you'd need it. Sometimes when you're just paralleling a generator with the utility, you have a single generator, you're paralleling it with the utility transformer. There's no, it's not combined generator systems. But there is circulating currents between the utility transformer, and the utility won't allow access to their neutral. Then really the only option you have is an NGI or an NGR. And again, we would recommend the NGI because of the triple frequency effect.
I believe this is our last question. How do you address existing NGRs on the generators?
Good question. A lot of times NGRs are used to limit the fault, intentionally limit the fault level of the power system. So if the fault level is too high and it's difficult to or expensive to provide protection, circuit breakers, and other protection systems for that generator system, then NGRs can be installed to either provide a high resistance grounding system or a low resistance grounding system, and now they're even looking at hybrid grounding systems, which are combinations of a low resistance and a high resistance. In those scenarios, you want the resistor in the circuit to limit the fault current. But if you have dissimilar pitch generators, or you have a generator with a utility where the voltage wave shapes are different, then you can still have high circulating currents. And the NGRs are typically not sized for continuous circulating currents. They're sized for instantaneous current during a fault. So you'd either have to put in a much more expensive NGR, which it will increase the losses in the system, because you've got I squared R losses for whatever residual current's going through the NGR. Or you can put in a DPNL to block the circulating currents, but then you'll still want to have the NGR in the system to limit fault current. So we can take the NGR, we can apply it to the X terminal on our DPNL and ground through the X terminal on our DPNL, and it will provide the fault limiting that you're intending with the application of the NGR, and you wouldn't have to worry about the excess current in the NGR. So I hope that answers those questions. We'll check once again to see if any other questions have come in.
There's a question, how are we going to receive the presentation with the recording today? Is that going to be sent?
Yes, so we've recorded the presentation, and that will be sent out to all registered attendees, even those who were not able to attend for one reason or another. We'll send it off to them as well, and we'll also post it on our website shortly.
And it will also be posted on the MIRUS YouTube channel. All right, that concludes our webinar, everyone. Thank you very much for attending and for all of your great questions. We will be sending out the recording of the webinar to you by the end of the week, and we'll look forward to chatting with you at the next webinar. Thank you very much.